Hello and welcome to Topic 7 of Mate 310 and 350 on optical properties of polymers. This is a three-part video series where we'll focus on the light refraction, absorption, reflection, and transmission in polymers. Light interactions are very important in polymers for a number of reasons. First of all, we're often interested in the transmission of light through the polymer for purposes of clarity. A good example of this would be fiber optic cables. The fiber optics inside the cable have to be clear to light in order to transmit the light and the data that's associated with that light. Reflection is another important attribute. Sometimes we want low reflection, such as in the case of a computer screen, in order to minimize glare. And sometimes we want higher reflection, such as the case of packaging, to make products look shiny and brilliant. And the final interaction with light is color production. So, for example, we might want a polymer that produces this particular color when it's illuminated from behind, such as in the case of taillights. An important property of all materials when it comes to light is that of the index of refraction. If light can travel through a substance, such as water, a gas, or in this case a polymer, the speed of that light will be decreased when it goes from moving from one substance, let's say air, into the second substance, in this case a polymer. This results in what's called the index of refraction, where the index of refraction is equal to the ratio of the speed of light through a vacuum divided by the speed of light through this second substance. And this is equal to the sine of theta I, which is the angle of incidence, the angle at which the light is approaching this first substance, divided by the sine of the reflection angle, the angle at which it travels through the second substance. So with this we can actually calculate the amount. If we know the index of refraction, we can calculate the amount the light will be bent as it travels into the second material. It's important to note that the index of refraction varies as a function of wavelength of light. So for example, if we look at glass, the index of refraction of glass is approximately 1.53 to 1.51 value. And this varies as a function of the wavelength of light. At low wavelengths of light, such as in the ultraviolet case, we have index of refraction as high as 1.53, so we get more bending of the light. But in the case of infrared light, at high wavelengths of light, we have a very low index of refraction and less bending of the light. The result is what we call the prismatic effect, where light enters into a prism and is scattered into the different wavelengths of light, revealing a rainbow effect, if you will. Polymer clarity is another important property of polymers for transmission of light. As a general rule, amorphous polymers are transparent, and increasing amounts of crystallinity in the polymer leads to more translucency, until eventually, as a polymer becomes nearly completely crystalline, it becomes opaque. This is because the polymer crystals are approximately the same size as the wavelength of light and therefore scatter the light. Good examples of transparent materials include polycarbonates, acrylics, and polystyrenes, all of which are amorphous because of their complex Merz structures and therefore transmit light. An exception to this rule is polyethylene terephthalate, which is clear but is also semi-crystalline. The reason the crystals don't block the light in this case is because the crystals are much larger than the wavelengths of light, again because of the complex nature of the PET Merz structure.